three missing numbers, so the fifth number or last number would be 144. Using the formula for geometric, the last number, a sub n, would be 144, equals a sub 1, the first number, which is 9, times the rate. We don't know what the rate is because we don't know what the second number is. And the exponent is n minus 1. We do know there's 5 numbers, so it would be 5 minus 1. To simplify this, we can divide by 9. 144 divided by 9 would be 16. And we'd have r to the fourth power. Find some number to the fourth power, which would be 16. That number would be 2, since 2 to the fourth power is 16. But it also could be negative 2, because negative 2 to the fourth power is also 16. So r would actually be plus or minus positive 2, which means r could be positive 2 or negative 2. The first answer for this question, if r is positive 2, 9 times 2 would be 18. 18 times 2 would be 36. 36 times 2 would be 72. And 72 times 2 would give us our final number, 144. If we multiply by a negative 2, the 18 could be positive or negative. Multiplying by a negative again would change us to positive 36, so that would stay the same. But multiplying by a negative 2, this could also be plus or minus 72. So our final answer, the three missing numbers, could be positive or negative 18, 36, and then positive or negative 72. Title of the first section is Find the Sum of a Geometric Series. Two equations or two formulas for the section. S sub n, or the sum of n terms. First equation is a sub 1, and inside parentheses, 1 minus r to the exponent of n divided by 1 minus r. Second equation, or second formula, S sub n, so again the sum of n terms, could also be a sub 1 minus a sub n times r divided by 1 minus r. Like the arithmetic series, there's two different formulas to find the sum, or S sub n. You can use either formula depending on the information that you're given. The first formula has n, the number of terms, and the second formula has a sub n, which would be the last term. First question, we have a sub 1 equals 2, r is equal to 3, and n is equal to 6. Looking at the three variables given, a sub 1, r, and n, we'll be using the first equation. So to solve for s sub n is equal to 6, so we'll be looking for the sum of 6 terms. A sub 1 would be 2, 1 minus r to the n exponent would be 1 minus 3 to the 6th power, divided by 1 minus r, which would be 1 minus 3. Solving this, 3 to the 6th power would be 729, and 1 minus 3 would be negative 2. 1 minus 729 would be negative 728. 2 divided by 2 would cancel out, and we're left with negative 728 divided by negative, which would equal positive 728. So the sum of the 6 terms for this geometric series would be 728. Second question, and last question for the section. A sub 1 equals 12. A sub 5 equals 972. And R is equal to negative 3. Again, looking at the 3 variables given, A sub 1 the first term, A sub 5, which is the last term, and R equals negative 3, we'll use the second sum formula that was listed. S sub n, which n would be 5, so we're looking for the sum of the first 5 terms. A sub 1 would be 12, minus A sub n, which is the same as A sub 5, would be 972, and times the rate R, which is negative 3, divided by 1 minus R, which would be 1 minus negative 3. Solving, we'd have 12, negative 972 times a negative 3 would be positive 2,916, and 1 minus a negative 3 would be 1 plus 3, which would be 4. 12 plus 2,916 would be 2,928 divided by 4, which would be 732. S sub 5, or the sum of the first 5 terms, would be 732. Title of the next section of notes is Find the Sum. Using a sequence. First problem, or first sequence, is 4096 minus 512 plus 64 minus ... as the sequence continues on. And we want to find the sum to 5 terms. So the first 3 numbers are given. We want to find the sum of the 5 terms for the sequence. Using the same formulas we just did, we can find A1, which is the first term. First term is the first number in the sequence, 4096. To find the rate for a geometric sequence, we'll take the second number divided by the first number, which is negative 512 divided by 4096. If we change that to a decimal, it comes out to 0.125. And the number of terms that we want to sum would be 5. Using the first formula that we did in the previous section, we'd have the sum of 5 terms, or S sub 5, equals A1, which is 4096, in parentheses 1 minus R, which is 0.125, to the n power, which would be 5, divided by 1 minus R, which is 1 minus 0.125. Solving this out, the sum of 5 terms, 4096, 0.125 to the 5th power, and this is actually a negative rate. 0.125 to the 5th power would be 0.4 zeros and a 3. And this would be negative since it's to the 5th power. Minusing a negative would be positive. 0.4 zeros and a 3. Divided by, and again this would be a negative in the denominator, so we'll be adding 1.125. Simplifying further, the sum of 5 terms, 4096, 1.0003 divided by 1.125. Using a calculator to multiply and then divide, the final answer would be 3,641. So the sum of the first 5 terms would be 3,641. Second question and last question for this section. We have the sigma notation. N starts at 1 and goes up to 9. And the equation is 5 times 2 to the exponent of n minus 1. For this problem, the formula is in geometric form, where we have a times 1, or a1 times n to the n minus 1 power. To find a1, the first term, again we can plug a 1 into the equation. 1 minus 1 would be 0. 2 to the 0 power would cancel out or equal 1, so our first term would be 5. To find the rate, again this formula is in the geometric form, a1 times r to the n minus 1 power, so r would equal 2. And the number of terms that we're looking for, from 1 through 9, would be 9 terms. Plugging these numbers into the formula, s sub 9 for 9 terms would be a1, which is 5, in parentheses, 1 minus r, r would be 2, and to the n power, which would be 9, divided by 1 minus r, which would be 1 minus 2. Solving this out, 2 to the 9th power would be 512, and 1 minus 512 would be negative 511, divided by 1 minus 2, which would be negative 1. Multiplying 5 times 511, that would be 2,555, and we'll have a negative divided by negative, which will give us a positive 2,555 for the sum of 9 terms. Last section today is called Find the First Term. Using a sum. First question and only question for this section. S sub n equals 165. A sub n equals 48, and r is equal to negative 2/3. Using the sum, the last term, and the rate, we can use the second formula that we did in the previous section and find what a sub 1 would be. S sub n, or the sum, would be 165, equals a sub 1, which is what we're looking for, minus a sub n, which is 48, times the rate, which is negative 2/3, divided by 1 minus r, which would be 1 minus a negative 2/3. Solving a single variable equation, we can isolate a1 and solve for the first term. 165 would stay the same. A sub 1 minus 48 times 2 would be 96. 96 divided by 3 would be 32. And we also have a negative times a negative, which would be a positive 32. Divided by 1 minus a negative 2/3. Minus a negative 2/3 would be adding 2/3. 1 plus 2/3 would be 1 and 2/3, or 5/3, 5/3. Solving from here, instead of dividing by 5/3, we can get rid of that by multiplying by 5/3 on both sides. 165 times 5 divided by 3 would be 275, equals a1 plus 32, and last step, subtract 32, and we have a1, the first term, is equal to 243. Title of the first section is Find the Sum of an infinite geometric sequence. The formula for this section is S, the sum, and since it's an infinite geometric sequence, there's no particular term number, it's the sum of all the terms. A1 divided by 1 minus r. And this equation only works when negative 1 is less than r is less than positive 1. For an infinite geometric sequence, which will be a sequence that continues forever, when the rate is between negative 1 and positive 1, the terms keep getting smaller and smaller, so we can approximate the sum of the entire sequence. If r is less than negative 1 or bigger than 1, the terms will continue to get bigger and bigger, and if the terms grow, we cannot approximate the sum. So the rate has to be between negative 1 and positive 1. The first problem we'll solve, a sub 1 equals 4, and the rate equals 5/7. So with the first term being 4, each term after that for the geometric sequence gets multiplied by 5/7, which again each term will get smaller and smaller, and we can use the formula to find or approximate the sum. So the sum of all the terms would be 4 divided by 1 minus 5/7, which is equal to 4. 1 minus 5/7 would be 2/7. And instead of dividing by 2/7, we can multiply by the reciprocal, 7 over 2. 4 times 7 would be 28, and 28 divided by 2 would be 14. So the sum of all the terms in the infinite geometric sequence is approximately or equal to 14. Second question, and last question for this section. The sequence is 1/2 plus 3 over 8 plus 9 over 32 plus ... as the sequence continues on. For this equation, we need the first term, a sub 1, which is the first number, 1/2. And we also need the rate, which we can find by taking the second number divided by the first number. So 3 over 8 divided by 1/2. And again, instead of dividing by 1/2, we can multiply by the reciprocal, 2 over 1, which would equal 6 over 8, which reduces to 3/4. Using the equation, the sum of all the terms in the infinite geometric sequence, a sub 1 would be 1/2 divided by 1 minus r, or 1 minus 3/4. 1/2 would stay the same. 1 minus 3/4 would be 1/4. And we can multiply by the reciprocal, which will give us 4 over 2, or just 2. So the sum of all the terms in this sequence would equal 2. Title of the next section is Write a decimal as a fraction. In this section, we'll take a decimal and rewrite that decimal as a fraction. First decimal we'll look at is 0.9. 0.9 is a decimal that terminates or ends, writing a terminating decimal as a fraction. The number 9 we put as top of the fraction for the numerator, and the first decimal place is the tenths place, so 0.9 is 9/10, or the fraction would be 9/10. Second question and second decimal, 0.7 with a line above the 7. A line above a decimal means this decimal repeats. So we'll change the decimal 0.7, which means these 7s will continue on. We'll change that to a fraction. Rewriting this, 0.7 with the line on top would be 0.7777, and I'll put ... as these 7s continue on forever. We can write each number as a fraction, taking the first 7. The first 7 would be 7 over the placeholder value, which is 10. So 0.7 would be 7 over 10. And what we can do is add to that each additional 7 afterwards. The second 7 would be 7. And the second decimal place, first decimal place would be the tenths. Second decimal place would be the hundredths. So the first 7 is 7 over 10. The second 7 is 7 over 100, or 7 hundredths. If we continue, the next 7, the place values, we have the tenths, the hundredths, and then the thousandths. So the third 7 would be 7 over 1,000. Put a plus sign and then ... This would continue on, as we'll have 7 over 10,000, 7 over 100,000, so on and so forth. Looking at these fractions represent a geometric sequence. Looking at the top numbers, the 7 would stay the same for every fraction, and the denominator going from 10, 100 to 1000. Each denominator is being multiplied by 10. So the rate for this geometric sequence would be 1, since the 7 stay the same, multiplying by 1 each time, and the denominator we're multiplying by 10 each time. A1, again the first value, the first fraction, would be 7 over 10. Once we have the rate and the first term, we can use the formula from the previous section. The sum of the infinite geometric sequence equals A1, which is 7 over 10, divided by 1 minus r. In this case, r is 1 over 10. Solving from here, 7/10 would stay the same. 1 minus 1/10 would be 9/10. And we have 7/10 divided by 9/10. Instead of dividing by 9 over 10, we can multiply by the reciprocal, which would be 10 over 9. 7 over 10 times 10 over 9. If you wanted to, you could cross cancel the 10s. And you'd be left with the final answer, the sum, 7 over 9. So looking back at the question, the decimal 0.7, where the 7's continue on, can be written as a fraction as 7 over 9. And the last problem for the section, last decimal, is 0.36, and the line will go on top of the 3 and the 6. The line again above a decimal means the decimal repeats, so we could rewrite this fraction or this decimal as 0.36, then the 36 repeats forever and ever afterwards, and we'll put ... as the decimal continues and does not terminate. Same steps as the previous problem. We can change each part of this as a fraction. If we have two numbers, 36, we'll take both of those for the fraction, 36. And the decimal place for the 36 will be the second decimal. The 3 is the tenths place. The 6 is the 100ths place. So the first 36 will be 36 over 100. And again, we can add to that each 36 as a separate fraction. The second 36, if you count the placeholders, tenths, hundredths, thousandths, and 10,000ths, the second 36 would be over 10,000. And one more will continue on, 36. The third 36. Counting the decimal spots, we have the tenths, hundredths, thousandths, 10,000ths, 100,000ths, and millionths. So the third 36 would be 36 over a million. After this, we can put ... as the fractions would continue on forever. Again, for the equation for the sum, we'll need the rate. Again, looking at the fractions, the 36 will stay the same for each fraction. So that means we're multiplying the numerator by 1. The denominator, we go from 100 to 10,000 to 1 million. If you look at the zeros that are added on, we're adding on 2 zeros each time. If we're adding on 2 zeros, that means we're multiplying by 100. So the rate for the sequence is 1 over 100. And A1, again, the first term, the first fraction, 36 over 100. Using the formula again, find the sum of an infinite geometric sequence. Starting with A1, which is 36 over 100, and dividing by 1 minus the rate, which would be 1 minus 1 over 100. Simplifying, 36 over 100 will stay the same. Divided by 1 minus 1 over 100.